This is a recording of the second half of the 6-2 uh, section, called 622, Transforming and Combining Random Variables. In this particular section, we're going to concentrate on the combining. In the earlier lecture, we talked about Pete's Jeeps and that Pete varies the number of passengers that arrive for his Jeep tours. We don't know on any given trip what that number of passengers is, but it ranges from two to six, two happening about 15% of the time, up to six, which only happens about 5% of the time. And in that lecture, we went through finding the mean for Pete's Jeep tours, the expected value. And we found it by doing a weighted average, multiplying 2 times 0.15, 3 times 0.25, 4 times 0.35, and then adding them all up. And this number represents over many, many Jeep tours, on average, how many passengers does Pete have? We also calculated the standard deviation. That calculation was a little bit more difficult, but we were able to do it based on the numbers in this distribution. Um, it happens that Pete has a sister, Erin, who lives in a tourist area in another part of the country and is impressed by the success of Pete's business, so she decides to join the business running tours on the same days that Pete um, does, but in a slightly smaller vehicle under the name Erin's Adventures. After a year of booking, Erin discovers that the number of passengers Y, as compared to passengers X for Pete's thing, Y for her half-day tour had the following distribution. Y, the number of passengers randomly selected for a half-day trip with Erin's Adventures, and it ranges from 2 to 5, 2 happening 30% of the time, 5 happening 10% of the time, and we could calculate her average number of passengers and her standard deviation. Now the question comes up, what happens if we take Pete's um, number of passengers and add it to Erin's number of passengers and create a new random variable which we will call t. And I might say t is found by taking one sample of Pete and another sample of Erin and adding those two random variables together. Well, since Pete expects 3.75 passengers per trip and Erin expects 3.10 numbers of passengers, we might say that the average of the total would be 3.75 plus 3.10 for a total of 6.85 passengers per trip. All right. Now, you say, well, I certainly hope that's true that you could just simply add those. But what I'd like to do is I'd like to try to convince you of this fact. So I made a little spreadsheet that's got um, things going on here. Um, and this spreadsheet randomly chooses a value of in Pete's distribution from 1 to 6, randomly chooses a value from Erin's distribution from 2 to 5, and it does so in such a way that it's uh, uh, consistent with the probabilities, the theoretical probabilities that were posted. And if I type in the number 1, you'll see that oh, this particular draw, Erin had 3 passengers and Pete had three passengers. On another day, they both had 5. It was a really good day. On another day, one of them had Erin had 2, but Pete had 3. Okay, and of course, what we could do for any of these days is that we could add up um, add up the sum of those two outcomes, the 2 for Erin and the 4 for Pete. And what you could see then, oh, sorry, I need to make that text visible. All right. That time, Erin had 4, Pete had 3, they're combined to 7. And again, I can make this look like we're getting different random draws all the time. Let me try this again. Okay, there's a three, a five, and it totals out to eight. Now, that's all well and good, um, except um, those are uh, just one random draw. Are we sure that we have, that this actually turns out the way we expected? So what I'm going to do is I'm going to show that I actually am not doing one random draw, but rather I am doing 10,000 of these draws. And I am having a hard time. Okay, so here are lots and lots of random draws from Aaron, and below here are going to be um, thousands of random draws from um, from Pete. And I did a little thing where we um, can actually see uh, if I do 10,000 of these random draws, do I get numbers that are close to what we theoretically expected? And that ended up being true. And I can do the same thing with Pete. And we could see that his numbers also are pretty close. And you notice every time I make a change to this spreadsheet, every time I make this, it does all new random draws, and we can see that these numbers are hovering around um, what we expect. And um, we could, from there, um, uh, calculate uh, the means and the uh, standard deviations of each of these. So here, thousands of 10,000 random draws, and we ended up right around what Aaron expected, 3.1. 10,000 random draws for Pete, and we ended up somewhere right around that 3.75. And those standard deviations are also really, really close. But what happens when we add numbers together? What happens when we add 3 and 2 and make a new distribution based on that 3 and 2, and then the 5 and the 4 and the 3 and the 3? Well, what we get is what I've hidden away over here, um, and that is uh, that 3 and 2 are adding up to 5. Well, let me hide this one. We don't need this one. We don't need this one yet. All right. We had the 3 and the 5. Of the 3 and the 2, we get 5. We had the 5 and the 4, we get 7. So here's 10,000 of these numbers, and they're all based on adding one random draw from Aaron and one random draw from Pete. And you can see with those random draws, we indeed end up at that 6.85, which is what we calculated to be the mean. And we're going to do some exploring on that. All right. So back to the notes. And in these notes basically says, hey, we can generalize this idea that if I'm creating a new random variable by adding two random variables together, if I want to find the expected value, that is, if I want to find the mean of that new random variable, I simply can add together the means of the two other random variables together. Okay? The mean of several random variables is the sum of their means, which means, hey, you don't have to go through the process of doing 10,000 random draws in order to show this is true. We're telling you this always works. All right. Now, let's go on to the next page. Okay. Next page. So let's think about this idea. The number of passengers on Pete's tour could be thought of as two, three, four, five, or six. And the number of passengers Y on Aaron's tour could be 2 or 3 or 4 or 5. And when we combine these in any way we want, the number of passengers that could be in the total number of passengers is some number from 2, 3, 4, 5, 6, 7, 8, 9, 10, or 11. Two getting, or sorry, not no two, no three. That's silly. Two coming from 2 plus 2. The highest number coming from 6 plus 5, and all the numbers in between can be found um, from there. What's the range of this set that the value t takes on? Well, range is found by taking the highest number and subtracting off the lowest number, and we end up getting 7. But let's compare that to the range of x. The range of x is 2 minus or 6 minus 2, which is 4. The range of y is 5 minus 2, which is 3. What happens when you add 4 plus 3? You get 7. Is that a coincidence? The answer is no, it's not. So that's one way to measure a spread range. We don't think it's a particularly good way of measuring spread, but it is a way of measuring spread. Is there some other way of measuring spread? Well, yeah, how about the standard deviation? Okay, the standard deviation uh, of this. Remember, the standard deviation had a really crazy formula. Um, the formula, by the way, that we're going to work towards is dependent on the variables being independent, meaning if I get told that Pete had a big day, he had 6 passengers, it'll have no effect on the probability that Aaron has either 2 or 5 passengers. They're independent. They're not affecting each other. All right. And again, with the formula that we're going to build towards is requires that the variables are independent. All right. And that's why in this narrative, Pete and Aaron live in different parts of the country. Well, let's take a look at what happens if we assume that independence. If we assume that independence, we get this really long table. Let me see if I can talk you through this table. Here's a value that Pete has in his a number of customers that Pete has on some random day. And here's an Aaron value. And each of those have their probabilities. We could say that the probability of having 4 passengers in this way is the product of 0.15 and 0.3, which ends up being 0.45. And therefore 0.45 ends up in that square. That's the only way to get a 4, a 2 and a 2, and that's the probability. Now, what about other ways? How about getting a 5? Well, we may get a 5 from a 2 and a 3, and I'm going to put a little check mark next to that one. Or we could get a 5 by getting uh, a 3 and a 2. And I'll put a check mark next to there. So the only way we could get a 5 is by those two methods. And if you add up those two probabilities, you get 0.135. All right. And then I could do this for each of them. I'm going to put a star next to all the places where you have exactly 6 passengers combined. And if you add up those 3 numbers, you get 0.235. I'll put a square next to all the places where you could get 7 passengers, and there should be 4 different ways that that could happen. Put the square here, put the star there, and if you add up those 4 numbers, you get 0.625. Okay. I'm just going to go ahead and write down the rest of the numbers for this distribution. I've already calculated them. And this is the textbook presentation of finding those values. I have a slightly different variation of this. in the spreadsheet that I was working on. And it looks something like this. It says, here's Aaron's outcomes, here's Pete's outcomes, and 2 and 2 happen at this intersection, and I find that value by multiplying those two probabilities together and putting them in the orange. Uh, all the place where there's this sort of pink, light pinkish color, pinkish orangish color, those are the two ways to get fives, and they total up there. The three ways to get sixes are in that next diagonal, so on and so forth. So that's how I finished off doing doing those. All right. So back to the um, uh, notes. It says we thought that the mean of that new random distribution t was going to be 6.85. I showed it through a simulation. Um, but what about the variance of this? Well, we were told that the standard deviation of x was 0.83843. And if I square this, I get a number, 0.889. Okay, if I do the same process, I could find the variance of y, 1.8, sorry, 1.181, right? Um, how do these numbers compare to the variance of t? Well, to do the variance t, I'm going to go back to the spreadsheet and I'm going to say, hey, here's this distribution of t, right? I'm going to expose these next rows, and show you that I've got a little formula here that's multiplying these two numbers, 4 and 0.0445, and that's like again data times the mean. Here's another data times mean, all those up, and we know that the expected value is the sum of those products. Oh, and there's that 685. Well, I did the same, but for variation, right? I did the same. Remember, the formula for variation or for variance is that I take a data value, subtract it by the mean, um, square that, and then multiply it by the probability. And you could probably see that embedded into this formula. Take the C8 value, 4, subtracted by the K11 value, that's the 685, square it, and then multiply it by C9, and there's your probability. And you'll probably recall that the sum of all those values is your variance, right? And that variance ends up being 2.078. Let's go back to the notes and put that in. 2.078. And it says, now do you see the relationship between this variance and this variance? Well, if I'm not mistaken, if I take this variance, 0.889, and I add it to this variance, 1.881, 1, 8 plus, or 9 plus 8 is 17, carry the 1. There's another 17, carry the 1. 1 plus 8 is 9 plus 1 is 0, carry the 1. Look at that. That number is really close to that number. And just remember that if you want to find the standard deviation, you take the value of the variance. You take the square root of that. And the square root of that variance is 1.44. Okay, so it's a little bit different. Okay, remember You can only add variances. You don't add standard deviations. The standard deviation of 0.943 and the standard deviation of y, which is um, oh, I'm sorry, standard deviation of Pete was 1.090, and the standard deviation of y was 0.93. If we add those together, we get three, carry the 1, 0, and so we end up getting um, a very different number than the real number, which is 1.44. So do not add standard deviations, add variances. Okay, so to summarize, for any two independent random variables, x and y, if you create a new distribution by adding up a random selection of x to a random selection of y, creating this new random variable t, that the variance of t is the sum of the other variances. Okay, and again, remember, add variances, not standard deviations. And remember that this law, this rule is requiring that the two random variables be independent.